Today's topic is Introduction to Laplace Transform. Then, what is Laplace Transform? When we talk about signals, there are two types of signals. One is discrete time signal and the second one is continuous time signals. To convert any time domain signals into frequency domain signal, we are going to use Laplace transform. The Laplace transform can be used in the case of continuous time signal. In case of discrete time signal, we are going to consider the another transform which is called Z transform. Clearly, Laplace transform can be converted the time domain signal into frequency domain signal. In a similar way, to convert the frequency domain signal into time domain signal, we are going to consider inverse Laplace transform, which will be discussed later. What are the applications of Laplace transform? Basically, the Laplace transform can be used to solve any linear ordinary differential equations. The advantage of this Laplace transform is directly we can find out what will be the particular solution of the given differential equations with the boundary values are given. Without finding the general solution of the given differential equation, we can find out what is the particular solution of the given differential equation. In a similar way, Laplace transform can be used in many engineering fields. Among those fields are signal processing, control system, integrated circuit, probability theory, and also it can be used in data mining or machine learning. Now let us define what is Laplace transform. If we consider any real valued function for all time t should be greater than or equal to 0 and the parameter s, either it should be a real or complex, then the integral between the limits 0 to infinity e power minus st f of t into dt is called Laplace transform of a function f of t, provided the integral should exist. It is denoted by L of f of t. Also, we can use one more notation that is called f of s. Suppose we wanted to find out the function f of t here. For that, we can use inverse Laplace transform. That is, inverse Laplace transform of f of s is equal to f of t. Now, let us consider some Laplace transform of elementary functions. Firstly, I am taking Laplace transform of the exponential function e power at with a is constant. By the definition of Laplace transform, here clearly f of t is e power at, then the Laplace transform of e power at is between the integral limits 0 to infinity e power minus st into e power at into dt. Now if you take t as a common factor because the bases are same, the powers can be added here. Then the given integral function becomes e power minus of s minus a into t into dt. The integration of e power minus of s minus a into t is e power minus of s minus a into t by minus of s minus a between the limits 0 to infinity. If you substitute the upper limit infinity and lower limit 0 here, will be getting 1 by s minus a provided s is greater than a. In particularly, if you take a is equal to 0 here, then e power at becomes 1. Then the Laplace transform of 1 becomes 1 by s with the region of convergence s is greater than 0. In a similar way, we are going to define the different trigonometric functions and polynomial functions by using the definition of Laplace transform. Here we have listed all the Laplace transforms here. Now you can see the Laplace transform of 1 is 1 by s with the region of convergence s is greater than 0. Laplace transform of e power at is 1 by s minus a with the region of convergence s is greater than a. Laplace transform of cos hyperbolic at is s by s square minus a square with the region of convergence s is greater than modulus of a. Laplace transform of sin hyperbolic at is a by s square minus a square with the region of convergence s is greater than modulus of a. If you consider the trigonometric functions like sin at, then the Laplace transform becomes a by s square plus a square with s is greater than 0. The Laplace transform of cos at is s by s square plus a square with s is greater than 0. Finally, the Laplace transform of the polynomial function t power n is gamma of n plus 1 by s power n plus 1 with the region of convergence s is greater than 0 and which is not defined for negative integers. Suppose here there is a particular case, if you take n is any positive integer, then gamma of n plus 1 becomes n factorial. So Laplace transform of t power n is n factorial by s power n plus 1 if n belongs to the positive integer. Now let us consider few examples to explain these elementary functions. In the first example, clearly the functions are given. We have to replace in place of the given functions by the corresponding Laplace transform. Here clearly Laplace transform of cos 3t is s by s square plus 9. Laplace transform of sin 4t is 4 by s square plus 16. Laplace transform of e power minus 2t is 1 by s plus 2. Laplace transform of 3 power t means we can express this 3 power t as in terms of an exponential function like e power log 3 into t. Then Laplace transform becomes 1 by s minus log 3. Finally, the Laplace transform of t cube is n is a positive integer. This becomes 3 factorial by s power 4. In the second example, it has given Laplace transform of 2t plus 3 whole square. Directly we cannot find out the Laplace transform of 2t plus 3 whole square, so that we have to express the given function as in terms of simple functions. On squaring the given 2t plus 3 whole square, we will be getting 4t square plus 12t plus 9. Now you take all the constant terms outside and you apply the Laplace transform. So if you take 4 outside, Laplace transform of t square is 2 factorial by s cube. Laplace transform of t is 1 factorial by s square. Similarly, the Laplace transform of the constant is 9 by s. In the third example, he has given sin t into sin phi t. For that, we have to apply sin A sin B formula. Sin A sin B is 1 by 2 into cos of A plus B minus cos of A minus B. Clearly, the given function can be reduced to cos function. Then, if we take Laplace transform of this function, cos 4t Laplace transform is s by s square plus 16 and cos 60 Laplace transform is s by s square plus 36. Finally, the Laplace transform of cos square of 2t minus 1 is, here we need to apply cos square theta formula, that is 1 plus cos 2 theta. Once after applying cos square theta formula, then again we have to simplify this cos of 4t minus 2 also by considering cos of a minus b formula, that is cos a cos b plus sin a sin b divided by 2. Finally, this cos 2 and sin 2 becomes constant terms and you write the Laplace transform of 1 is 1 by s, Laplace transform of cos 4t is s by s square plus 16, cos 2 is constant, again sin 2 is constant, Laplace transform of sin 4t is 4 by s square plus 16. Thank you.